We have arrived at a final session, and our final speaker of the day is Director of Technology at KED 42. He's been in Drupal for nearly 14 years. He built his first Drupal module while he was in Goa. Please welcome Piyuesh Kumar.
Thanks, Ruturaj. I started with Drupal as an intern, as Ruturaj mentioned, and the community has kept it going so far. So, kudos to the Drupal community. All right. How do we start? So, I think everyone has been enjoying the event so far. Yes, I had a couple of learnings yesterday. I was speaking with a couple of folks. I spoke with Tanay about HTML slides, and that's where last night I vibe coded my entire slides to this version which you're seeing here. All it needed was like giving my old slides ka PDF to Claude Code and giving a screenshot of Oaisys homepage. I asked it pretty much to generate an HTML slides as well as use the color scheme from the screenshot that I provided to you. And if you notice the color code, it matches the black and red. It's all coming from the oasis.com. So yeah, I think I have had my own learnings, the takeaways for me from the event, and I'm sure all of you have some. Initially, the plan was to dive a lot deeper into how to post-train LLMs, but based on some conversations during the event, I've tweaked the format a little bit. I'm going to talk about when not to post-train your models, or rather, what is a good use case where it would make more sense for post-training your a model. Because all of it is expensive. It's going to be expensive in terms of cost. It's going to be expensive in terms of time spent. And then if you don't really have that output, it all goes into vain, right? So my talk here is basically going to be more focused about when not to post train, understand the LLM architecture a little bit, understand a couple of terminologies which get used very frequently in the ML training ecosystem. All of us use Chat GPT every other day, right? I mean, to generate code, to write emails, to do a number of stuffs in our daily life. But ever wondered how what's happening under the hood? How is it generating that output for you? So at some point, at some times you would find Chat GPT to be responding correctly, but at some times you would also see it confidently lying about something which is not right, right? Which means that this is not necessarily generating the right response for you, right? Something is happening under the hood, which is what we'll take a look at. So today's talk, we're going to start with a couple of busting slides. We'll talk a little bit about what should be a decision framework in order to make a choice when to post train. We'll look at an ML glossary, which is basically the kind of common terms which get utilized in the ML world. We understand how the LLM architecture has evolved over time, what happens under the hood behind large language models. Post-training methods, of course, we're going to take a look at a very short demo which I prepared last night. I trained a very small, tiny model to be able to do something, which we'll take a look at. And other methods which are available in the ecosystem for post-training. And then finally, we will do a wrap with the key takeaways as a part of this talk. Starting with the first one. So fine-tuning is equals to adding knowledge. How many of you think that when you're fine-tuning a model, or for example, if you're giving, let's assume this use case wherein you're giving ChatGPT your Q4 ka budget ka data, for assuming you're working with a company where you need some analysis to be done on Q4 budget, or maybe just some generation that needs to be done on the Q4 budget. Do you think that it memorizes all the numbers, or does something else happen in the hood? So it learns the data is what he's saying. Any other thoughts on this? So this is what happens. The reality is fine-tuning is teaching your model a pattern, basically. It's a mathematical pattern that it's learning. It's not actually learning that this is a fact, but rather based on the fine tuning, it's able to understand that this may be the probable output when someone has asked this question from me. Okay. So it's not, so LLMs don't understand facts, but they understand patterns. Every query that you send to your LLM, it's trying to run n number of iterations, generating n number of outputs with different probabilities, right? And then whichever output has the highest probability, that's what you get as a response back. So it's all a game of probability. The ideal solution for this scenario would be you convert your Q4, or you basically vectorize your Q4 ka reports, and then use a RAG system to be able to generate responses. Basically, if you want to supply a fact to your models, use RAG. The second one is, if you are adding more and more data to your model, it makes it a better model. So one important metric behind the data is the quality of this data. If you're training, or if you're giving your model a lot of gibberish data, you're basically going to be reducing its output accuracy. So 100 records of good data is much better than 10,000 rows of gibberish data that you're giving it to. So yeah, I mean, it's very similar to for an exam you're reading up on the internet, rather than focusing on few specific curated data set, curated books or curated chapters. Another one is RAG. I mean, there's a notion that RAG is not basically making my model learn, which is correct, which is a fair assumption. But that's also something which pushes a lot of people back in terms of using RAG for certain use cases they're really, really suitable for. So, RAG is something that you should always and always prefer using if your data is changing very frequently, because you cannot keep training your model again and again and again on new data. You need citations, basically, which is pointing back to a source of truth, that this is where I'm getting this response from, basically instilling more confidence in end users. And yeah, you want to avoid more and more hallucinations because you're working on a more deterministic. So you're fetching deterministic data from your vector store and then passing it to LLM to generate an output based on the data that it has found deterministically. This one is very common. I mean, I've had multiple conversations with a lot of people, and often this is also asked from customers that how do I ensure that my outputs are very contained? They're not. I mean, how do you avoid your model from generating something which it should not? And this is basically coming back from a notion that you can train away. With training, you can avoid your models from hallucinating. The hard truth is, and this is the basic reality behind all LLMs. Hallucination is not a bug, but it's a feature of LLM due to which it's being able to be creative. It's able to generate new and new responses every other time. What you can do is you can control the outputs with better prompting. There are a lot of prompting techniques, like you have a few shots, you have chain of thoughts, and the multiple other ways in which you can control the write a better prompt. Use RAG for real grounding. Use guardrails for with your prompt to be able to bound your uh, LLMs from responding back to something you don't really want it to. And most importantly, teach your applications to say, I don't know if it doesn't have any response about the data, because this is one of the most important things. If it goes back and tries to respond back with something from the internet, from its own knowledge, whereas this content is not even available on your website, it becomes a difficult thing for the customers to rely on. This is again another common pattern which I think I've seen, is we end up giving incomplete prompts to LLMs. Like, for example, we go ahead and say that just make this text sound more professional. For you, the meaning of professional may mean something else. For someone else, it may mean something else. For the LLM, it may mean something else. And in this case, the generation may completely go out of the way. If your prompt is vague, your output will be vague. Simple. Taking a very simple real world example, this is one requirement which we were discussing with a customer recently. Um, they had they had a support project as a part of their Jira backlog, and their ask was, "Can you train a custom model for us, which should be able to respond back based on the queries that have been asked or issues that have been solved by developers in the past?" When we went into the consulting phase with them, we did speak with them about why do you really want to do a custom training on this data set. It's going to be expensive for sure. It's going to be time taking, right? And it may be able, in the end, we may have an output which is accurate. We may also be into a situation wherein after the training, we might need to retrain, do certain adjustments for it to be able to get to the right state. While if I take all of your Jira tickets, its summaries, and push it into a vector database, right? Not only you'll be able to get the output that you desire today, but also if tomorrow a new Jira ticket has been created, it will feed back into the RAG system, and you wouldn't really need to retrain your model based on that. So what I'm trying to get to is there is a cost. There's a time factor associated with model trainings. We should be very mindful whenever we are taking this decision. In today's world, your LLMs are way more powerful, and with with the right prompting techniques with RAG, you should be able to get your problem statement solved. There are very few cases, for example, wherein you're dealing with a very small model and you're dealing with a very narrow domain, because these models, these LLMs are trained on general data. Let's assume that you want a very specific use case wherein you're dealing with something in fintech industry or the medical industry, right? You don't really want, you want very narrow, very grounded responses, right? Or you want an offline model to exist on a device which probably gets used in a place with low network conditions, right? Those are the cases where you should look at training a small model with this data set. Again, the key word here is small model. Training a large language model with data sets would require you to have huge data set for it to be able to make any kind of an impact. Use a small model with a curated data set. Do start with fine tuning, and then you should be able to get to something which is small enough to fit into devices and run offline. We'll talk about more use cases as we advance through the slides. So, yeah, I'll quickly summarizing the different techniques that we saw as a part of previous slides. Prompt engineering, it's not a lot of effort. Probably it's going to increase your prompt by a couple of lines, which may increase your token usage a little bit. But it's not free, but yeah, it's going to add to a little bit of cost, very little cost. When you use RAG, there is going to be a cost associated with it, but then you're using it in cases where you have a dynamic knowledge, where you need to have a dynamic knowledge base. Use fine tuning wherein you want your model to be trained on a new pattern. RLHF, DPO, I'll come back to it towards the end of the slides. These are reinforcement learning techniques, which are expensive, which are more time consuming. It may take weeks to months to get it to work correctly. And these are primarily useful in cases where user preference matters a lot to you. You want very personalized outputs being generated from your model. In those cases, they come into picture. We'll talk about it. So the conclusion here is start with the cheapest option that you have there. Move down the ladder, and if the previous layer doesn't fit your use case, then only move to the next one. Because the closer you're moving towards fine tuning, the more problems that you're increasing for yourself. This is a very simple summarization of the same slide. For dynamic data, we use this. Most important part is the third one, which we didn't cover in the previous slide. So there are also use cases wherein you may see your model, because again, your model, so 2 into 2 is equals to 4 is not something that is understood by your model as a fact. For it, 2 into 2 is equals to 5 is also a possible response, but has a much lower probability. That's the reason why the output that gets generated is 4 for you. So if logical use cases are there, use deterministic approach to it, use logics, use function calling, use tool calling for those use cases. We'll quickly go through a couple of terminologies that are primarily, like, very frequently used with ML models. Model is nothing but a brain. I think we have talked about model a lot. Tokens is something that we keep hearing multiple times, right? Tokens are chunked parts of a huge sentence, right? The better tokenization that you will have, your model will have, the more chances for it is to be, so the more creative it will be, basically, because then it can mix and match. So for example, I am planning to go to Delhi, right? Now planning is a word which can be one token, but at the same time plan and ing could be two different tokens here, right? With, if the plan and ing gets broken into two different tokens, your vocab increases for your model. So now your model understands plan as a separate word, versus in the previous use case it would have understood planning as as a single word. So it can use plan as a word now, while it couldn't have used planning as another word. Okay, so tokenization is nothing but it's basically a way of breaking down your sentences into chunks. Embeddings, I'm sure most of you would be aware of, sure, right? It's basically converting your tokens or tokens into machine readable vectors, weights, or parameters. We so if you have looked at making a choice about a model, you would have read that this is a 3V parameter model, this is a 4M parameter model, right? What does this parameter mean? So the more parameters your model has, the more capabilities it has in terms of being able to tune the output. Attention. All of you would have seen this word as a part of different goodies on the event as well. Like, you've seen the badge, it says attention is all that matters. You've seen it on the bag, attention is all that matters. So, okay, I'll take a quick example here. There's a huge paragraph, there's a big paragraph of 2, 3 statements, right? My model is reading sentences in different sequence lengths. Okay. Now, what happens in first paragraph? I have said that Piyush is traveling to Delhi. In the second paragraph, I go ahead and say that he is going to be in Delhi for 2 months, while while the second sentence is being understood, he needs to relate to Piyush, right? And this is what the attention span of a model means. With different so certain words, when they are augmented in different sentences, they may mean different things, right? Like a river bank may mean something else, while a HDFC bank may mean something else. So that's what attention allows you to do. Training is basically uh, a process through which your model learns new patterns. Inference is basically using the model to generate something. Labels are basically the parameters or data points, basically, which your model is learning. Overfitting and underfitting are two different situations in which you can run into while training the model. Underfitting is a situation wherein your model has learned, but it has not learned to respond back on all different parameters. Overfitting is a situation wherein your model has learned the data. It has not learned the pattern. Parameters, I think we've already spoken about. And bias is basically, it's a it's a symptom in your data set where you may have a biased data. So let's assume that you're talking about a classification model ka training, wherein you want to classify certain text as spam versus not spam, right? Now, if your data set itself is skewed, and let's assume that your entire CSV file has almost 10,000 records, but you have 2,000 records which are spam, while 8,000 records are not spam. It's a skewed data set, right? And would cause your model training to get biased towards one classification. For how LLMs actually work, what I would do is, so this is a very interesting video which I found on which I always refer to people as well, for someone who's basically getting started with LLMs to understand how LLMs function. And what I would try to do is, I'll try to keep it on mute and voiceover. So over here, what we're looking at is, yeah, assume that this is a piece of of paper where there's an instruction. It's a half-tone paper, wherein you have some text written, and you're expected to understand from an AI assistant what could be the output of it, right? What you typically do is you work with a chatbot, you pass it to the GPT assistant or whatever, and it takes care of generating. How does it do that, right? So what it's doing is it's basically identifying the next token based on the brain that it has, based on what data it has been trained upon, and then it continues to do that as a feedback loop, continues to pass the previously generated output as a feedback, generating the next most probable word, forming the response. When we say Paris is a city in France, it's not a fact that it understands. Basically, so it's gonna get n number of responses with different probabilities, as I said. So this is what I was talking about. When you give this as a query, it takes care of generating multiple outputs with different probabilities, right? Since France has the highest probability, that's what gets returned as a response. That's typically how LLMs work. Yeah, we spoke about parameters. Uh, you see those small knobs there uh, in the screen in the screen. Each of these are parameters which can be tuned with different weights to be able to tune the model to be able to generate the right response for you. So during the training, what happens is your weights for these parameters keep getting updated based on, yeah, they keep getting updated. I'll come back to the rationale on which these weights get updated, but the weights keep getting updated, and based on the weights getting updated, the probability of different words which are getting rendered as an output, they keep getting changed, right? Towards the end, we reach a state wherein we have something which should be the output, or which is closer to the output, and that's where we say that our model has been trained on this data set. So it's going to show this with a very nice visualization. So you notice that the probability of different words is changing while your model is getting trained, and these are different layers, and these are so every small knob that you see there is a parameter. Imagine the number of parameters your large language models would have this way, right? And imagine the kind of compute it would take to train a large language model if you were trying to fine tune it. So the idea behind showing this video was to make you visualize the kind of compute, the kind of effort, the kind of time it's gonna go into training a large language model. So what I did last night is I took a very tiny model, Distal GPT-2, which is like 200, 300 MB in size. I took a small data set, which is a SMS spam data set available in Kaggle. The data set is very small, like it has 5,000 different rows. We ran an eval on the base model, which is Distal GPT-2, trained completely on web scraped content. So this is basically a generation model. It doesn't understand anything about classification at this stage. The baseline model was run against a couple of evaluation metrics. You notice the output, it says accuracy is 85.7%. That's a false positive. And it's very likely that you may run into these kind of cases and you'll have to vet this out. The F1 score, on the contrary, it says 0.0, which is a more legit way or more known way in the industry today to evaluate your model's accuracy. When we ran it through the SFT, which is supervised fine tuning process, the accuracy jumped to 99.1%. F1 score, it jumped to 96.8%, and we will quickly take a look at. By the way, I took a screenshot of, just for fun's sake. I was trying to train this on CPU, and if you take a look at the screenshot, I'm not very sure if it's visible at the back. But if you look at this piece where I was trying to train the same model, the time remaining is 71 hours, 40 minutes to train on a data set of 5,000 records. And while this was running, this was the status of my system resources. So all of my cores were busy. Still, it would take a huge amount of time. And that's where I switched to Google Colab, uh, ran the same model on a GPU, which finished in like 15-20 minutes. So this is what I wanted to, at a very high level, I'll try to run through this. The idea is not to dive deeper into it, but so a couple of libraries which were required to be installed, Kaggle API keys. We downloaded this data set from Kaggle. Basically, we were reading the data set to ensure that it has data, and it has data in what format. We ran into a couple of, not a number. So went through data preprocessing, cleaning phase, and now we have a data set which is ready to be trained against. We loaded the Distill GPT-2 model, and the next step was to break down your entire data set into 3 different chunks, which is like your training data set, your validation data set, and test data set. So your CSV file of 5,000 records was broken down into 3 different chunks. So one of these chunks is something that we will use for training, another chunk which we'll use for validation and testing. Further down, if you look at it, yeah, over here as well, we were looking at this. This is where we ran the eval for our model, and we used OneDB for the evaluation. And the evaluation accuracy, which we were looking at on the slides, was coming from here. You can set up your training arguments, which would basically help you tweak your training parameters in a way. The training it ran for some time. We ran 3 different epochs. So epochs is basically how many times you want to run training on the same data set. Because with every run, your weights for different parameters are going to be changing, leading to different kind of outputs, maybe moving to the right direction, maybe not moving to the right direction. Usually, there's a loss function with and a graph during training. In an ideal situation, your loss graph should look like this: something which is high at the top and slowly going down. If that's happening in most of the scenarios, your model would have trained correctly. Now, as a part of demo, what we had done is 4 or 5 different SMS simulations here. Before this, I would jump below, wherein I was trying to run the same data set on the baseline model, which was my Distill GPT-2. So when I tried running those, if you notice this SMS, which is congratulations, you've won $1,000 gift card, claim your prize now, sounds very much like a spam. The model said that it's not a spam message with a probability of 70% almost, right? Which means that my initial baseline model didn't know how to classify the messages correctly, right? Now evaluation after post training, we tried running the same set of questions again, and now if you take a look at it, the same SMS message is getting classified as a spam with a 99.94%, 99.49% probability. So this, not just this, but we also try to plot the accuracy graph later down the line. And although 86%, which was getting returned by my eval metrics, was not a right data, but we can definitely see that there's a jump in the accuracy here. This was done for a simulation use case. In a real world scenario, you would not be training on such a small data set ever, right? And this was just to showcase the process that usually will get followed in the fine tuning. So this is a sequence diagram which I prepared, showing different participants during the training process. The set of tokenized messages get passed in batches of 16 messages because that's the batch size we chose. The predictions are computed. The predictions are compared against the actual outputs by loss function. Initially, your loss will always be high, which will drop down slowly over time. The other component here is optimizer, which is responsible for updating the weights. Now, this is where your optimizer is responsible for tuning down the weights now, tuning the weights. Now, since your weights have changed, the outputs would change, moving it towards ideally towards a better output. And this is epoch 1. Since our epoch count was set to 3, we have we run the same process 3 times. Whichever has the highest accuracy, that gets returned as my final model. And that's the final model against which we have run the final set of queries. So the two different, at a very high level, SFT is one fine-tuning tactic, and another one is preference. So in a quick nutshell, the few common pitfalls to avoid. The first one is do not train without a baseline. Think about what is your use case. What are a few constraints around which you want to train? Like, do you want a 2B parameter? Do you want a 1M parameter? What are a few constraints around which you want to train? What's your baseline? So your model is, so SFT is basically going to teach your model a pattern, not data. So keep that in mind, that your model is not a fact house, but it understands the patterns. And it's all a game of probability. The next token, whichever has the highest probability, will be getting returned. Do not ignore the data quality. Make sure your data pre-processing step takes care of cleaning up your data, because if I had those NANs in my data set, my outputs would have looked different. And the very first step should always be like, go down the stages as we looked at the previous slides. Start with prompt engineering, try out RAG. If none of them work out, then only switch to fine tuning. And when not to post train, like again, if you don't have good quality examples, if you have not tried writing better prompts, do not chase benchmarks. Basically, you should not be training to put your model on a leaderboard, but rather solving an actual use case, because you're wasting the time and resources both. Make sure that you have a clear success. I'm repeating myself on last few slides. But yeah, this is what the cheat sheet should look like. Start with a why. Make sure that you run an evaluation initially before training, so that you have a baseline where you're starting from. Use the right recipe for training for the right use case. Curate your data. Make sure that you're working with clean data. Run evals after every step, so that you know that where your model stands in terms of the metrics that you're evaluating it against. And if you've done it right, you will end up with a right assistant. Yeah, post training isn't magic. It's basically cooking with the right set of ingredients to get the right thing out. Cool. Thank you, everyone.